Okay, up to here we are familiar with center of mass, and we also know how to obtain center of mass for various systems. So now we are going to discuss motion of center of mass, and as we proceed, you will come to know that why it is important. So let's start with this term. Let's say total mass of a system. So we have given n number of particles, n number of particles. So total mass of the system times this position vector for center of mass. We can write it as sum of these things from I equals to 1 to n, and then we will have the same thing in expanded form. So it will be m2 r2, and we have n number of particles in this system, so it will be mn rn vector. So this is total mass of the system. This is position vector for center of mass, and this is mass of first particle times position vector of the first particle, and then it continues. Okay. Now we can do one thing, and remember we are taking these masses to be constant, means m1, m2, and all these masses are constant. So we can do one thing, we can differentiate both sides, means we can take time derivative. So m dr by dt equals to m1 dr1 by dt plus m2 dr2 by dt, so on up to nth particle. So here we have this thing, and we know that time derivative of position vector gives us velocity vector. So we can write m1 v1 plus m2 v2 plus up to nth term. So v in. And what about if we take one more derivative here? Again, time derivative of these things. So we will get, okay, so we will get here m acceleration vector. We know this thing, time derivative of velocity vector gives us acceleration vector. So ma equals to m1 a1 plus m2 a2 plus so on up to mn, and here the acceleration vector of nth particle. Now this thing we can write force on the first particle plus force on the second particle, and here force on the nth particle. Here F1 is net force acting on the first particle. So this net force includes total internal forces as well as external forces. Internal forces means the forces which are being exerted on the first particle due to the second particle or third particle or up to nth particle. And external forces are the forces exerted on this first particle due to some other factors which are outside of this system. So external forces. So this is net force acting on the first particle. And same argument you can carry on for all these things, and including this also. This is net force acting on the center of mass here. Now, if we focus on this term, total mass and times acceleration of the center of mass, and then this is F net on the center of mass. So this F net includes only external forces, means the sum of external forces, vector sum of external forces. So now you may think why I have omitted this In here, I am saying that F1, F2, F3, all these forces are including internal and external forces. But when I am talking about the center of mass, I am saying that this F net is nothing but sum of all the external forces. So I can write it F external. And I have justification for this. Let us take three particles, means a system of three particles. Let's say this is particle, first particle, this is second particle, this is third particle. And now, if we want to know what is the net internal force on this system altogether. So let me find out what are the forces, internal forces acting on each and every particle. So on the first particle, there is one force which is force on the first particle due to the second particle. And let's say these forces are gravitational forces for time being. And the second force, which is internal force acting on the first particle, is due to the third particle. So on the first particle, there are two forces acting. Now, we know if there is one force acting on this particle due to the second particle, the first particle will also exert the same amount of force but just in opposite direction. So we can say this second body is experiencing a force due to this first body. And in the same way, here also you can say that the third particle is also experiencing a force due to the first particle. And now what about these two pairs? So these two pairs we have done. And now what about this second and third particle? So here there is force on second particle due to the third particle and force on the third particle due to second particle. And now, if you sum all of these forces, you will get net force 0 because these two forces, for example, F12 and F21, these forces are equal in magnitude and opposite in sign. So if you combine these two forces, the net force will be 0. And this will be happening for all the pairs which you have created for this system of particles. For example, we have only three particles, so we have three different pairs of this kind. And if you take sum of all these things, you will get each pair 0, 0, 0, net force 0. So net internal force will be 0 if we are taking all the particles of the system. So what is left here? In case of center of mass, this net force is only external force. So we are not going to bother about what are the internal forces, what are the interactions between two particles, means whatever happening internally in terms of force, we are not going to bother when we are studying about the motion of center of mass. Okay, from here we can deduce a very important statement that the center of mass of a system of particles moves as if all the mass of the system was concentrated at the center of mass and all the external forces were applied at that point. What does it mean? It means we can consider this center of mass as it has all the mass concentrated at this point, and we can consider that net external force is acting on this center of mass, and then we can determine its motion. By doing this, we are now able to reduce this n number of particles problem into a single particle problem at the first. Now let's take an example for this. So let's say we have thrown a projectile here. So let's say this is a projectile which has been thrown here at some initial velocity u, making some angle here, and let's say acceleration due to gravity is here. Now, what are you expecting to be its path? It should follow this parabolic path. Okay. And what happens if this projectile moves and during its motion, at some point, let's say here, this projectile explodes. So here, let's say explosion happened and it gets fragmented into two parts. Let's say from here, there is one part. Let's say this is first part of this projectile and this is second part. Now its motion is complicated. Earlier, it was a single particle and it was moving along this trajectory, and you could easily identify that this projectile is going to follow this trajectory and it will end up here, or maybe any other parameter you can easily find out. But when it explodes into two different parts, its motion is now complicated. But if we know that it has center of mass here, and we know that center of mass is not going to be affected, means the motion of center of mass is not going to be affected due to any internal event happening. So you can easily say, okay, the center of mass of this body will continue its initial journey, means it will continue as this projectile. No matter where this part goes and where this part goes, this center of mass is going to follow the same trajectory and it is going to end up here. Now, center of mass is a kind of conceptual thing here. So you may not see anything coming at this point, but center of mass will lie. And these two particles will move such a way that they always keep the center of mass on this trajectory only. So in this way, because the only external force acting on the center of mass is the gravitational force here. So the motion of the center of mass will be as a motion of projectile. Now moving ahead, now you might be thinking, okay, we know the motion of center of mass, this is okay, but these two particles are now following different motion. And what about these two particles? Because they are not going to follow the same. So we have solution for this also. Okay. But before that, now we are going to study linear momentum of a system of particles. So what is the linear momentum? We all know that total linear momentum can be written as, for n number of particles, sum of all the linear momentum for each and every particle. And then we can say this is the linear momentum of center of mass. And we can write here m1 v1, as we know. We can write here m2 v2 plus up to mn vn. And this is going to be p all. That is mass times, as we have already obtained this thing. So if you want to see that thing, I can bring it back here. So here we have, where, okay, here we have obtained this thing already. Let's get back to the point. Yes. So we can write it as momentum of center of mass. Now, what about taking time derivative of this thing? This will give us m dv by dt, and then it will be m a, or you can say f external. Once again, I'm saying we have obtained all these things. So finally, we can write dp by dt is f external. And in case f external is 0, then dp by dt is 0, or you can say, and this p is a constant. So you can say that if there is no external force acting on the system, the linear momentum of the center of mass of that system is constant. And this is, you can say, conservation of linear momentum. Okay. Now, this is vector, and if we want to get some more information, we can write in its component form, and we know that these components are independent to each other. So we can write here equals to some constant, and as we know, these components are independent to each other. So here we can write this is some constant C1, this is some constant C2, and this is some constant C3. And you should not worry about this thing. Why I am saying these three coefficients are linearly independent here? We have already discussed about this thing. Because these three vectors are orthogonal to each other, so they are not going to give any projection. Any component is not going to give any projection to onto the other component, so they are independent. Now we can continue that discussion we left earlier, that in this particular case, look, yes, in this particular case, when this projectile moves, it is following this path. Up to here, it is okay. You can easily say, okay, this entire system is going to follow this path. But after explosion, one part is going to this direction, another part is going to this direction, and then the motion becomes complicated. And we focused on the motion of the center of mass only. So there must be some inclusion so that we can find out about these two also. This is what we are going to include now. Okay, so by changing the reference frame, we can include those things also. And how can we do that? Let's take two different examples where we are going to do the same. The first example we are going to take, let's say we have a radium nucleus here, and this nucleus is moving with a constant velocity for timing. And at this point, this nucleus splits into two different nuclei. One is helium nucleus, you can say alpha particle, and another is radon. So we have two different nuclei here after breaking down this radium nucleus. And what about center of mass? So the center of mass will follow the same line. It will keep moving with constant velocity. And let's say it is here for time being. So this is one frame. If we are talking about this incident in laboratory frame, we can say that this is the motion of center of mass happening here. And now this is laboratory frame of reference. Now, in second case, what we can do, we can take a reference frame with respect to which this center of mass is at rest. Means if this center of mass is moving with some velocity u, we can take a reference frame which is also moving with the same velocity u along the same direction. Or we can keep our observer here at the center of mass only. Means theoretically, I am saying we can keep our observer here. So what will happen in that case? This is the situation when we observe this from laboratory frame of reference, and now we are going to observe with a frame of reference with respect to which this center of mass is at rest. And this can be happen when a frame of reference is moving with the same velocity, or the observer is at the center of mass. And in this case, what will happen? Here we have center of mass, and this observer will observe that this helium nucleus is moving towards this direction, and this red dawn nucleus is moving towards this direction. And what we have done? We have escaped from this velocity now. So we can say, from here we can say what is the position of helium nucleus now, or alpha particle now, what is the position of this radon particle now. So we have solved that problem also. These particles are now, we can obtain the variables about their motion. So what we have done ultimately, this entire complicated motion, we have just separated into two different parts. In the first part, we are observing the motion of center of mass, and in the second case, we are observing the motion of the particles while taking center of mass as reference, or a frame of reference with which this center of mass is at rest. So combining these two things, you can say what is the position of this particle or what is the position of this particle after certain time t. So this is approach where we can solve this kind of complicated things. And let's take one more example regarding this, and then we will end this discussion for now. So in the second case, we have a binary system of stars. So binary system where two stars move about a common center of mass. Yes, it should be. Okay. So what if this binary system has a kind of motion like this? Let's say this star is moving this way, and this second star will also continue to move about this center of mass. So they are just revolving around the center of mass. So if you observe these two stars from center of mass, you will see these two stars are just revolving on certain path about this center of mass. And if you observe not from a frame of reference which is at center of mass or which is such that center of mass is at rest, so in that case you will observe this complicated helical motion. So what we can do? We can separate in the same way as we have done earlier. We can separate it as first part where we will observe the motion of center of mass, and then we will take another frame of reference, and then from this frame of reference we will observe the position or the motion of these two stars, keeping center of mass as reference, or maybe a reference frame which is moving as fast and in the same direction as the center of mass is moving. So in this way, we can combine these two things to arrive at the things where we can find out the positions of these two stars after certain time t. So this is all for this video. In the next video, we will start a cross product of vectors, which is necessary to proceed further. So in the next video, we are going to start cross product or vector product of two vectors. So this is all for this video.